Hello everyone. In this video, we're going to take a look at a question called Escape Room from last year's CCC competition. It's a Senior 2 question. Many people consider it as the hardest Senior 2 ever. I also think so. It's pretty hard, to be honest, for Senior 2. So, also, I want to mention that for all Senior 2s, they require a little bit of observation to make to get a full score. If you have a really brute force solution, it can only get like partial marks. Okay, let's get into this problem. So I'll show you the problem statement first, and you can take a minute to read it and try to come up with a solution on your own. And in the following part of the video, I'm just gonna explain it. So feel free to pause the video. Also, a suggestion from me is that if you are just practicing, be sure to give you 30 minutes to think about each problem. Just don't give up once you couldn't, once you don't have no idea. So the more you think, and the more you will benefit when you are reading solution or watching videos like this. Okay. Okay, let me explain this problem then. So you are given a grid such as this one. So it is a screenshot of the sample input. And you gotta determine how can you, could you, if it's possible to travel from top left to bottom right. And of course you can travel from top left to bottom right if you're just moving up, down, left, right. However, in this case, you couldn't do that. You are following a set of rules of moving in the grid. So the rule is, if you are placed in a cell, that cell has a number. It can be 3, 10, 8, 14, and you can move to grids that have their coordinates product equals to the cell's number, your current cell's number, which sounds confusing, but let me make an example. So you have a 3. So you can move to all the grids, their products between their row number and column number equals to 3. So you can move to 1, 3, and 3, 1, because 1 times 3 equals to 3. 3 times 1 equals to 3 as well. Which means you can move to 8 and 6. From those points, let's say you are on 8, you can move to 2, 4, and 4, 2. So 4, 2 isn't even in the grid, so we just don't consider it. So we go to 12, and 12 we can move to 9, because 3, 4. The product is 12, which means we can, in this grid, travel from top left to bottom right. So we just output yes as our output. If we cannot travel to the bottom right, we just output no. So it's like yes or no. It's small case. Okay, lowercase. So these are the approaches I think most people will come up with. So the first one is try to, also for this problem, I think you should immediately notice that it is a graph traversal question. So which means you will use DFS or BFS algorithm to deal with this problem. So if you don't know DFS and BFS, so they just spells as how they sound, DFS or BFS. So if you don't know them, be sure to check them out on Geek4Geeks or HackerRank. HackerRank has pretty good videos to explain them. So they are just basically graph traversal algorithms. So for this problem, these two algorithms is necessary to know. So if you don't know them, be sure to check them out first. So from now on, I will assume you know BFS and DFS. However, so for Euro DFS or BFS, we know we can just move up, down, left, right. But now, in this case, we have to look for children nodes on our own. So which means the hard part of this problem is to identify or to form an adjacency list, to identify the children nodes of each cell. So how can we identify the children nodes? I think like most people will come up with these approaches. So the first approach is to try to factor v. So v is like each number. So if you have a 12, you just try to factor it and check if they're in the grid. However, this one is quite slow because you're dealing with time complexity of n squared times square root of 1e6. So it's 10 to the power of 6. Which is too big for our computer to handle in 1 second or 2 seconds. The second approach is to loop through the grid and try to find the children nodes. So what I mean by that, if you have a number like 3, you just go through all the coordinates and you multiply the row number and column number. You check if the product equals to the current cells number or not. So if you have a 3 on hand, you just go from this cell to that cell, that cell, that cell, and you just go to every cells, and you check if row times column equals to 3 or not. If equals to 3, it means it is a children node. Okay. If it doesn't equals to 3, then you just ignore it. It doesn't matter. However, it should be approach 2. However, this algorithm is still quite slow because it has a time complexity of n to the power of 4. So it is, in this case, it is 10 to the power of 12, which is way too slow for our problem. Means not for score, which is not good. So what our enhancement we can make to this approach is that we can try to stop doing the repetitive work. So instead of going every cell and check the entire grid, we can just check some grid. We can just do it once, so we don't have to check it every time, and we can store it in an adjacency list. So we just avoid doing the repetitive work. So this one is actually like a snake oil thing, because whenever you try to optimize your code, just try to cut down the repetitive work, and it will always benefit you. Also, we need the data structure to handle our children nodes, and we will make an adjacency list. Then that's our approach. So let's try to implement this in real code. So my code will be in C++. I will consider to make Java video and even Python video if maybe, not sure about that, but currently I'm just gonna do C++ solution first because I'm really comfortable in this language. Include bits std C++. So even if you don't know C++, it's okay to watch because it's pretty similar to Java, both like syntactically and yeah, in almost every way. They're basically the same, like for competitive programming. Row and column. So we're taking the input for them. So let's create 2 vectors to store input. One to store input, the other to store Boolean values, like serve as the purpose of a visited array, so we don't have to visit the thing again, visit a single cell again and again. So when we visit it, we just mark it false. Mark it true. So when the second time we reach there, we don't have to care about that. We just ignore it. So and I think the visited array thing is pretty basic for DFS and BFS algorithm. You almost use it every time you do graph traversal questions. Okay, so let's take in the inputs. So for int I equals to 0. Hold on, should I? Oh yeah, let me just make indexing start from 1, because we have to handle like the producting, and it will just make it easier. So I plus plus for int j equals to 1, j is smaller than column, j plus plus as well. So let's make a variable called val and sing val. Okay. And grid ij equals to val. Also, we need to do adjacency listing. So vector pair int. So we need pair here because our coordinate contains two number, like both the column number and row number. So let's call it adj equals to vector pair int. Oops, forgot a thing. Okay, let's make a size of. Wait, do I have to do this, or I can just? I don't know. Okay, I think it's big enough. So now what do? So we just put the thing in the adjacency list. Put the current coordinate into adj I times j. So when we have the value of I times j, the product of I times j, so we know we can travel to this coordinate. So adj dot push back and make pair ij. Okay, so that's our adjacency list, and now we're just gonna do a BFS. So let's call it Q. I mean not Q, not calling it Q, but it's a Q. So let's call it BFS. And we push the starting coordinate to the Q, so push make pair 1 1. So while BFS dot empty is false, it means we have something to explore. So okay, so we create a current one. So the following thing is pretty basic BFS implementation. BFS dot front, BFS dot pop. And we have to check if our current if cur equals to the bottom right, so we can check if the row number equals to the row total row, like the number of the row in the grid. Instead, it just means the bottom right. So if cur dot seconds equals to 12. So if this happens, we just return from the program, means in the program. But before do that, we'll just gotta see out yes. And the default case is no. If we couldn't find any path to escape, we just print no. So otherwise, if it's on the bottom right, let's try to explore it. Okay, so for pair, let's use auto auto next in ADJ if visited next dot first next dot second is unvisited. If it's unvisited, so we just push it into the queue. Let's push it into the queue. So bfs dot push next, and we mark it true, so we don't have to visit it again. Okay, so let's try to run a sample, see if this one works. Wait, hold on. Oh, it's ADJ grid, so we have to get the index of that thing. So what is the index? The index is the current V of the cell. So the current number of the cell. And how do we get the current number? So it is current coordinate. We just took it from the coordinate 2D vector or 2D array of variants using Java or Python. Okay, so let's try to run our sample. Oops. 0. We have multiple mistakes, so let's try to correct them one by one. Oh, item J. Okay, it says our sample is wrong. Also we have to check visited I11 first, because that's where we start. I just open some random stuff just to check how far our program can run. Okay, it's for a segmentation fault. Is it like me adding 2 zeros over there? Oops. Yep. That's a mistake. The vector is declared too small. Okay. Looks like we pass a sample. Let's try to run our program. And as you can see, all the test case passes. Okay, so we have segmentation fault. Okay, let's try to correct the mistake. But first we have to identify it. So I think it's like this vector is too small. Let's submit again. I think this can resolve the issue. Okay, as you can see, all the test cases passes. So thank you for watching. Okay, let me just do a little brief conclusion. So for this problem, the first thing you should be able to do is to just know BFS and DFS very well, because that's the base of this problem, and it would just grant you some partial mark even if you couldn't make the observation. So so after you know the BFS and DFS and able to implement them, for this problem you also need to notice the repetitive work you are doing if you are using brute force, and to come up with a smart solution you have to avoid it. So in this case I use I just pre-compute them, and when I'm actually doing the BFS or DFS, here in this case it's BFS. So when I'm doing DFS, I can do it instantly just look it up from my adjacency list, so which saves a lot of time. Yeah, so thank you for watching. Bye.